we know, so far, what we know is how to project one function onto the direction of another function, right? Onto a single direction. We have this nice projection formula that lets us do that. That doesn't tell us, at least not right out of the chute, how to project onto the span of multiple functions, right? Which is what you're being asked to do in part D of question number 1. So let's tackle that first. So if we go back to the first half of the semester, this is the equivalent to having, for example, a two-dimensional plane that we would like to project onto, and figuring out how to project onto a two-dimensional plane. So here's a plane, P. And I have some point that's not on P. Hint, hint, let me say. Not in P. So I have this point, and I'd like to figure out how to project that point onto the plane. Whoops. So I need to find its projection. Projection of B onto the plane P. Right? So it turns out, just as it was in the first half of the semester, that if I have a basis for my plane, let's call them V1 and V2, and I know how to project B onto both V1 and V2 individually, and, this is a big and, if V1 and V2 are orthogonal to one another, then how do I do that? So, to project B onto the span of V1 and V2, which is the plane P here, if V1 and V2 are orthogonal, all we need to do is add the projections onto V1 and onto V2. Onto V1 and V2. And again, this works if V1 is orthogonal to V2. So there's a reason that I have you do parts A and B before you do part C and D on the homework, is that if you want to do that same thing in the realm of projecting functions onto other functions, you can, as long as the functions onto which you're projecting are orthogonal, mutually orthogonal. So if this collection of functions is an orthogonal set, then just take the sum of the projections onto each of the phi n's, where that sum runs over whatever indices that we need it to run over. So that's the first thing, is that if I want to project onto the span of even infinitely many functions, right, in order to do that, I just need to project onto each one of them individually and add them together, provided that those functions are an orthogonal set, if they form an orthogonal set. If we happen to know, and this is something that I'll give you for free for now, but we're going to want to verify it on Wednesday, if we happen to know that all of these sines of n pi L over x are an orthogonal system of functions, we have to verify that. If we do verify that, then we'll be able to find these coefficients a sub n just by projecting onto each one of the sine of n pi L over x's. So the projection, according to our projection formula, is just going to be sine of n pi x over L, so phi n, times the ratio of the inner product of f with phi n, or phi n with f, it doesn't matter because they're symmetric, right, divided by the product of phi n with itself, the inner product of phi n with itself. And so to find out what a sub n should be, a sub n is exactly this ratio of inner products. And if we unpack what that is, that's just going to be the integral from 0 to L of the product of f of x times the sine of n pi x over L. That integral, of course, taken with respect to x. And then we're dividing that integral by the integral from 0 to L of sine of n pi x over L times itself, so sine squared of n pi x over L. The good part is that the integral in the denominator here doesn't depend on the function f, so we can just crank out what is the integral from 0 to L of sine squared of n pi x over L To do that, we need a trigonometric identity that shows us how to exchange sine squared for 1 minus the cosine of twice n pi l over x, n pi over l times x, multiplied by a half. So we use a trig identity just like you do in Calc 2 to evaluate the integral in the denominator. When you do that, you find out that the integral in the denominator comes out to pi over 2. Which is kind of interesting because it doesn't depend on n. Right? Regardless of what n is, that integral in the denominator always comes out to pi over 2, which is kind of interesting. So the norm, the magnitude of the function sine of n pi over l times x is always square root of pi halves, regardless of the value of n. But then the numerator is just this integral of f of x times the sine of n pi x over l. So if I were to give us a takeaway for today, for how to determine the right a sub n's, these are called the Fourier sine coefficients. And the series that they piece together is called the Fourier sine series of the function f. Fourier sine coefficients. They're defined by a sub n is equal to, I'm going to take the division by pi over 2 here in the denominator and just flip it to make it a multiplication by 2 over pi, multiplying the integral from 0 to L of f of x sine of n pi over L times x dx. Gives us the Fourier sine coefficients of f of x on the interval from 0 to L. Question? So what we do with those numbers is we stick them here in our solution to this initial boundary value problem. So if I crank this out and I get some expression that has n's in it, the goal is then to put that expression into the series to complete the solution of our initial and boundary value problem. That's where we're ultimately going with all of these. So just to kind of connect the puzzle pieces, these will go there once you've computed them, and they will build our finished solution for this IBVP.